Synthesizing full-body hand-object interactions is challenging because the motion of the entire body, the fingers and the object need to be generated without violating physical constraints. Recent research has shown promising results in synthesizing hand-object interactions. Goal method models only the approaching phase, while IMOS focuses on the object manipulation phase. However, these methods are data-driven and can cause artifacts such as interpenetration or foot skating. In this paper, we introduce the first physics-based method to synthesize dexterous full-body grasping. We model the entire sequence of approaching, grasping and manipulating an unseen object. Furthermore, our approach enables the important task of trajectory tracking. For example, we can generate walking motions along a given trajectory. During this motion, agent can carry and then move the object. It does so by following a wrist trajectory. The inputs to our task are a static hand pose reference and a route and wrist trajectory. Our goal is to generate the motion of a human character that approaches and grasps the object, and then moves the object by following the trajectory. The task can be divided into two phases, an approaching phase and an object manipulation phase. In the approaching phase, the human walks towards the object and obtains a grasp. In the object manipulation phase, the human interacts with the object. Our method leverages reinforcement learning and physics simulations. Therefore, we simulate the motions of the human and object in a physics simulation. We propose a two-stage hierarchical training procedure. We divide our model into learning of skill priors and high-level training with these priors. We decouple the skill priors into a body prior and hand prior and train them separately. They are trained from reference motion capture data with adversarial training. Body prior policy predicts the target joint angles of our simulated human body. The hand prior policy predicts the target joint angles of the simulated right hand. We then update the state of the physics simulation by driving the human and hand models to these predictions. We then train a hand-object interaction policy by leveraging the body and hand prior. The hand-object interaction policy predicts the latent skill vectors for both prior policies and additionally the route and wrist target for the body prior. We introduce a reward function that incentivizes the policy to achieve full-body hand-object manipulations. It combines an adversarial objective with a task reward. The task reward promotes the policy to follow the hand pose reference and the trajectory. Finally, the synthesized motions in the physics simulation can be exported and replayed in the simplex parametric space. We now present results. We compare our method against goal in the approaching phase and IMOS in the manipulation phase. Goal method models the phase from T-pose to object grasping. IMOS generates motions after object grasping. Our method models the full sequence of approaching and manipulation. Goal often penetrates the object before grasping. IMOS also suffers from interpenetration artifacts. In contrast, our method resolves such artifacts due to the explicit use of a physics simulation. We find similar behavior across different objects. This is also reflected in our quantitative results, which show better physics-based properties. Other artifacts of data-driven methods are foot skating and ground penetration. Our method successfully removes such artifacts. We show that our method can generate the entire sequence of approaching, grasping, and manipulation for different unseen objects. Furthermore, we can generate a wrist trajectory and make our human character follow it. In this example, we show a zigzag trajectory. We can also define a route trajectory after the object is lifted. This will generate a walking motion while the object is carried. Failure cases of our method occur with large objects. Objects like the binoculars, the piggy bank or the large cube are such examples. The fingers need to be fully stretched out to grasp the object. In future work, a policy for two-handed grasping could alleviate such failure cases. In summary, we propose the first physics-based method for full-body dexterous grasping. We introduce a two-stage hierarchical training procedure that leverages a physics simulation. We show that our model generates motions with less physical artifacts than the baselines. Our model can grasp unseen objects and enables test-time trajectory to move the human and the object. Thanks for watching.